So my name is Anil and I am TA of this course. So those who are new to this course, to this uh, session, so in the last class we solved the assignment 1. So in this class we won't solve the assignment, but we will see the basics of the semiconductor devices. Semiconductor actually, not the devices. We will not move to the devices now. So in the last class someone asked me about the if we can do something on the lithography part. So I am thinking I will cover a small portion of the lithography in after the devices will be started in the class. Okay, so if I will start now, that won't benefit you now. So today we will see some basics of the semiconductors. So in the last class we have seen the Fermi Dirac distribution and something band diagrams, band EK diagram, band and conduction band and valency band, all these things. So so do you remember the Fermi function? So I am assuming you might be knowing, or if you don't know, I will write it down. So this is the f of E, Fermi function. Fermi function is nothing but it gives the probability of finding an electron at that energy level E. Okay, Fermi function is nothing but it gives the probability of finding an electron at energy level E. So it is given by, this is the Fermi Dirac distribution, distribution, and it is given by f E is equal to 1 plus exponential of E minus EF divided by KT. This K is nothing, K is the Boltzmann constant, KB we can say KB. Okay, so this is nothing but this is the Boltzmann constant. So what this expression gives is what is the probability of finding an electron? Finding an electron is like, what is the probability that the state at energy E will be filled by an electron? This is the it will give this thing. Okay, so I think someone wants to join the. Okay, let me admit. Yeah. Okay, so in this class we will see the density of states, because we need to see the density of states so that we can see how many electrons are there in the conduction band and how many holes are there in the valency band. Okay, whenever we see electrons, whenever we talk about the electrons, we always see how many electrons are there in the conduction band, because if the electrons will be in the conduction band, they are only the electrons in the conduction band are only are only, okay, just a minute, are only moving in the lattice. Okay, because they are in the unbound state. Not in the unbound state, we can say that there are energy levels, empty energy levels, so that they can move in the another energy levels, so they can move in the lattice. Okay, so we will see the density of states function, how we can calculate the density of states, and how can we calculate the number of electron, we can say the electron density per centimeter square in semiconductor. Okay, so there are 13 students. So do you remember that energy, this Fermi level EF? What is EF? EF is nothing but this is just a statistical distribution, statistical approach, so that we can make the equations easier, make our task easier for to solve the equations. Okay, so Fermi level gives the probabilistic distribution of the electrons in the conduction band and holes in the valency band. So it gives the distribution of electrons or holes. Okay, so that by definition we can say the Fermi level is at any temperature. So if there is the probability of finding an electron at the point at the energy level is 50%. So that is the energy, Fermi energy level. Okay. So someone was asking to join. No one is there. Okay. So do you remember that direct band gap and indirect band gap semiconductors? I hope you might be knowing. So let me tell you just one thing. A small background about that. Okay. So if there is an semiconductor with EK diagram. Okay. Okay. This is the like energy. This is in the K. So if this is the conduction band and this is the valency band, conduction band and valency band. So if the maxima of the valency band and minima of the conduction band lie for the same value of K, lies at the same value K of K, so then this is a direct band gap direct band gap semiconductor. Okay. And if this valency band and this conduction band and valency band lie at the different values of K, this is K, this is E. So if this lies at the different values of K, this is the K1, this is the K2. So if they lies at the different values of K, so whenever an electron transit from this point to this point, it has to go with the change in momentum, change in the lattice momentum. Okay, so it will transit with the change in momentum. So this is the indirect band gap semiconductor. Okay. So now what we will calculate is, okay, how can I add one more slide actually? Okay, I don't know how to add the slide in this one. So let me go to another thing. Wait for a minute. Okay, it is not working. Okay. Stop. Just wait for 2 minutes. I am just okay. Okay. I think in this one you can see, right? Huh. Okay. I don't know how to. Okay. So now you can see, right? So now we will see the density of states here. Okay. Huh. So now we will see the density of states here. So why we are calculating the density of states? So that we can calculate the number of electrons, the electron density in the semiconductor. Because we need the electron density to to understand the semiconductor devices. Okay, to make new devices and all. So okay, let me see if someone is there. Yeah. Okay. So to find the number of electrons in conduction band or number of holes in the valency band, so what we do is we have the Fermi Dirac distribution. So probability of finding an electron at any energy level E. So f of E is there. We have f of E and we have density function. So like here in every notebook or in every book, so it is represented by G of E. Okay, so if we multiply the density of states with the probability of occupying that state of occupying a state, so if we multiply these, we can find the density of states. We can find the number electron density Ne. Okay, number of electrons per unit number per centimeter cube. Okay, so we can find that thing. So that's why we are calculating this. So in textbooks, so how this so I think in class also it is not covered that G of E, the solution of G of E is not covered. How can we find the density of states? So I will also not be covering this because this is out of scope of this fundamentals of semiconductor devices, because this is for the basics only. So if anyone needs, we can go through that also in the next class. So if anyone need the derivation for this GE, we can calculate it in the next session. If anyone, just drop me a message, so I will cover that also. So GE is the density of states, which is given by 4 pi by h cube into 2m star. Okay, 2m star 3 by 2. So it is given by this formula and square root of E. So this is the density of states. So so can you see the density of states is a function of square root of E, and it is dependent on the mass of this effective mass of the electron or hole. So this is irrespective of E, whether it is in the conduction band or the valency band. Conduction band, we calculate the electron density of the states for the electrons, and for valency band we calculate the density of the states for the holes. Okay, so in the new slide. Okay, yeah. Okay, so this is the, so how this is this distribution will look like in the, if I will show you in the graph. So that was given by, okay, it is G of E is equal to 4 pi by h cube into 2m star raised to power 3 by 2 square root of into square root of E minus EC if we are calculating for the density of states in the conduction band. So in the last class, it was not covered in the last class actually. E minus EC. So it is the square root of the function is this density of states varies with the square root of the E minus EC, or we can say this is the GE, this is E, this is in this x-axis is the E energy, and this is in the y-axis we are taking density of states. Okay, so the graph will look like this. Okay, so it is a parabolic, this is a parabolic. Okay, this is parabolic if GE ka square, G, if we say G of E square is directly proportional to E minus EC. Okay, so this is the kind of parabola only, nothing else. Okay, so we are starting at here because of there is a band gap between E conduction band and the valency band. If we go in this direction, so we will find this EV and EC. So that will also be, if okay, I can write that one also. Yeah, this is the biggest headache. Okay, density of states for electrons. I will explicitly write that density of electron states for electrons, GEN is equal to 4 pi by h cube into 2 m n star. This is the effective mass of the electron, ME or MN, we can say. ME will be fine, ME and MN doesn't matter, raised to power 3 by 2 square root of E minus EC. Okay, and GP, density of holes, density of states for the holes, is equal to 4 pi by h cube into 2 mp star 3 by 2 and square root of EV minus E. Okay, so this is the thing. So this is how we can calculate. This is the G of E or G of E, and both we can say. So this is EC, this is EV. Okay, so and this is the band gap, easy. So now we have seen that thing. So this is the density of states graph. Okay. Someone wants to join. Okay. So does anyone have any doubt in this case? So now we can calculate the, if anyone has the doubt till here, they can ask me, because this I think sir already taught, so I am just repeating that thing, just because if you didn't understand in that class, you can ask me. Okay, so just directly ask me, because I cannot see if any hands are raised or anything, so I cannot see that. So just ask me directly. Okay, so as I told you, so the number of electrons number of electrons n can be calculated the with the multiplication of Fe into Ge. So this will be number of electrons per unit area per unit energy it will come. So Ge has the Ge is the density of states per unit volume per unit energy. Okay, the density of states in the range of energy, that dE, or that it has like, okay, Ge has the this say units per unit electron volt per unit centimeter cube. So but we are calculating number of electrons. Okay, number of electrons, so we need to integrate. This is in the conduction band, so this is in the conduction band. So for per unit energy, that you can see in the EK diagram. Okay, so in that diagram, so what is the density of states for with the per unit energy? Okay, so in this graph, so what is the density of states with per unit energy of, this is the E. Okay, let me check, someone wants to join that. Okay. So we need to, so how can we calculate? So for a semiconductor, for a piece of semiconductor, what is the density of electrons in that semiconductor? That is like per centimeter cube, how many electrons are there in that how many electrons are there in that semiconductor. So what we need to do is we need to integrate, because energy is the reciprocal, is in the reciprocal space. So we are converting that into the real space. So how we are calculating the number of electrons per unit volume? So we need to integrate it from EC to infinity, because energy is, any electron can have energy above this. Okay, so this is the conduction band, this is the valency band, and electrons can have energy above this. So what is the density of states? What is the number of electrons? So how we are calculating it? We are calculating at this point only, this point. Okay, so but we integrate it from till infinity. So dE. Okay, so if we want to calculate number of holes per unit volume, so we need to calculate the holes in the so holes will be the like from minus infinity to EV. So F of E, probability of finding a hole, F of E, or 1 minus Fe, actually 1 minus F of E into G of E. So this was, Fe was the probability of finding an electron. What will be 1 minus Fe? 1 minus Fe will be nothing but it is the vacancy. What is the probability of finding not finding an electron? That is the hole. Okay, so a hole is nothing but a vacancy of the electron. So that's why we take 1 minus Fe. Okay, by solving these two equations, we can find N and P, number of electrons and number of holes in a semiconductor. Okay. So okay, let us solve for that one. So N is equal to EC to infinity. We need to integrate 4 to find the density of electrons. EC to infinity. Fe was nothing. Okay, Ge, whatever, say Ge or Fe. First we will take the Ge. 4 pi by h cube into 2m star 2mn star. N is the effective mass of electron, 2mn star raised to power 3 by 2 into square root of E minus, or we say EC or E minus EC. Okay, into now the Fermi-Dirac distribution function Fe is 1 over 1 plus exponential of E minus EC divided by kBt. Okay, so actually this is really very complex equation to solve. So there are some assumptions, but currently we are not taking that. So there are some assumptions. If this E minus EC is this the gap between this what we say is more than E minus EC is greater than 3 kBt. So we take the assumption about Fermi-Dirac assumption, or I forgot the name of that assumption. So we directly can take this, can be converted directly to, can be approximated directly to exponential of E minus EC divided by kBt. This 1 by 1 plus exponential of E minus EC by kBt can be approximated to exponential of E minus EC by kBt if the difference between these E minus EC, this difference is greater than 3 kBt. Okay, so this can be approximated to this value. So okay. So after solving this one, n is equal to n. Actually we are not solving the integral now, but we can because solving that integral it is really very headache. So what we are saying is, we can now, I am not solving the integral, I am writing directly the answer of that integral, because I cannot solve that integral, that is out of my scope. So n is equal to nc into, so I will come on in this f1 by 2 into exponential of, this is the Fermi function EC, okay, got EC minus EF by kBt. Okay, this is the Fermi integral. Actually this NC is nothing but the effective density of states. Effective density of states we are calling it because we are this NC, the density of states, we have seen that this is EK diagram, right? This is E, this is K, and the effective density of states at this point, at the bottom of the conduction band, at this point, this effective the density of states is represented by NC. Okay, so this is nothing but the effective density of states. Okay, so why we are taking this is, like, we are calculating the number of electrons at this bottom only. So because the density of states, so okay, in the next we will come when we solve the graphical representation. Okay, so Okay, so I will show that why it is coming, why we are seeing this one. Okay. Mm, this is f of e. Okay, this is e, this is f of e. Huh. Yes, wearing out. Huh. That I need to just f of this e, this is ef, and this is 1. Okay, 1 by 2. At any temperature below. Okay. Okay, this is EC. Okay. So density of states is starting from here. Okay, I will take a new slide. Okay, so what we are saying is density of states, if we represent this E and this is FE or whatever we say, so this is the EC. Density of states are going like this, and this is EV. Density of states for the holes are going like this. So, and our Fermi function also, this is the EF. Fermi function for K for at any temperature. Fermi function is this FE. This is FE. This is value of FE is 1. Here I am just actually I will come on to this later, because I am just shifting this diagram at 90 degree. I just wanted to show how can I calculate that thing. So FE, let's say this is 1, FE is 1, this is 1 by 2. At for 0 degrees I am just okay. This is GE, this is also GE. If I am okay, actually it will come like this only. Okay, the Fermi function will come like, okay, will come like this only. So actually the what we were doing is n, we were calculating n, so the density of electrons. So density of states function is this one, and density of electrons is nothing but the multiplication of this EF and GE, this GE. So the multiplication of in the regime of energy will be nothing, this this N is equal to F G into G of E into F of E in energy regime. So this was the multiplication. Actually, I was turning it into the 90-degree so that I can show you in the energy regime in the vertical axis and Fe in the right, in the x-axis. So I was a bit confused in this one, but it is like this only. So the multiplication, this Fe will be, this will be smeared out at the at temperatures greater than 0 Kelvin. So at 0 Kelvin, I am taking the another this pen. So at 0 Kelvin, it will be this. Okay, I don't know why it is not. At 0 Kelvin, can you see the yellow one? So below EF, the probability of finding an electron is 1. So this was the portion. And for probability of finding an electron above EF at 0 Kelvin, it was 0. So at temperatures greater than 0 Kelvin, what will happen is it will go above. It will go above this one, this red one. Can you see? And it will, this Fermi function will overlap at the above EC will the density of functions. So the multiplication of this Fermi function with the density of density of states will give us the number of electrons. Okay. So I'm really sorry, I might have confused you. So if you have any doubt in this one, you can ask me, because I'm sorry, really I might have confused you in this one. Okay. Now I will keep a very basic thing, because this is like confusion in this one. So I will keep at the very basic. So it is not necessary, actually. This thing is not necessary. So let us go to the very basics, not in the mathematics but in the very basics, how we can with the Fermi level, how the electrons and holes, the concentration of the electrons and holes changes in the semiconductor. Okay, so let us see that. So if this is the conduction band and this is the valency band, EC and EV, so always so there is, this is the band gap. Band gap is, this is the band gap. So in band gap in between EC and EV, what we say is there are no energy states. Okay, no energy states. Whatever states are there for the electrons, the energy states are available above EC and below EV. Okay, so there are no energy states. So this is the Fermi level. The Fermi level will lie always in the at the middle of the band gap. This is Eg by 2 and this is also Eg by 2. Okay, the Fermi level will always be lie in the at the intrinsic. So what is the meaning of the intrinsic is if there is no impurity added. So we are not doping the semiconductor. That means the intrinsic semiconductor. If we dope the semiconductor, then we are altering the concentration of holes, or we are altering the concentration of the electrons. So by adding impurity, we see the electron. We change the conductivity of the material by increasing the number of holes or by increasing the number of the electrons. If so, at what we have said is at EF, at energy EF, the finding of the probability of finding an electron is 1 by 2. So at EF, probability of finding the electron is 50%, that is 1 by 2. So finding an electron is 1 by 2. Also the finding an hole is also 1 by 2. So PE or NE, NE and PE, I am writing this probability of finding an hole and probability of finding an electron. So NE or PE, so this is 1 minus FE, nothing but 1 minus FE. This is equal to FE. Okay, so probability of finding an hole or electron is 1 by 2 at this point. So at any temperature T, if this is my E and this is FE. Okay, next slide. Okay, this is E, this is FE. FE is, I am just writing. Okay, so this is not related to the Venn diagram. This is, I am writing for the for probability of electrons in the conduction band. Probability distribution I am writing, just probabilistic distribution. Okay, this is the conduction band, this is the valency band, VB, this is the conduction band. So this is, if okay, someone wants to join. Okay, so this is EF. Now this is EF. So okay, now I will show you. This is 1, this is 1 by 2. This Fermi function will be like this at 0 Kelvin. So if we increase the temperature, what will happen is this Fermi function will be like this. Okay, this Fermi function, if we increase temperature more, the Fermi function will smear out more. It will be like this. It will be 1 by 2 at EF and it will be like this. So with the increase of temperature, the overlap of this Fermi function with the conduction band is more. If we increase the temperature more, it will go like this. If it increase the temperature more, it will go like this. The overlap, what I am saying is overlap with the conduction band. The density of states in the conduction band GE at this point is it is the value of this FE is more. FE is more, so the density of electrons Ne will be more. Okay, N, not Ne, N will be more. Okay, if we increase the temperature, this this Fermi function will smear out more. So more and more smearing out. So we are increasing the concentration of electrons in the conduction band. Okay, this is electrons. Okay, we are increasing so in the valency band also, this Fe, or say 1 minus Fe, it is increasing. The value of 1 minus Fe is increasing with the overlap with this density of states GE in the valency band. It is increasing. GE into 1 minus Fe is increasing. So also the number of holes are also increasing. If both will increase if it is intrinsic semiconductor. Okay, so let us say if our Fermi function is at this level. Okay, so what will happen is EF is at this level. It is closer to the conduction band. Okay, if it is closer to the conduction band, so overlap with the conduction band will be more, but overlap with the valency band it will decrease. Okay, the of this Fermi function will decrease, so it will the n will be greater than p. Okay, in the semiconductor, number of electrons will be greater than p. Okay, so it is n type semiconductor. N type semiconductor, it is done on by deliberately, it is done deliberately, no, with by adding the dopants or impurities. It cannot happen like for the intrinsic semiconductor as so it cannot happen it cannot happen. We need to dope the semiconductor to make it more uh, electrons in the conduction band. So this is how we change the conductivity of the material. Okay, so if we dope, if the conduction, if the Fermi energy is not here but here below the this is, we can say, EI, EI, intrinsic Fermi level. So if the Fermi level is below the intrinsic Fermi level, so number of holes will be more, P will be more than N. Okay, P will be more than N, so it will be a P type semiconductor. Okay. Actually, I am teaching for the first time, so I don't know how to like make you understand all these things. If you will ask me question, I definitely can go more deeper into the, and I can tell in a different way. If you are not understanding, just let me know. Okay, so huh. And one more thing is, whenever we calculate the number of electrons or number of holes, so if this is the conduction band, CB conduction band, and this is the valency band, and this is the EI. Okay, EI. So how can we say that this is the N type or P type semiconductor? So if the conduction, if the Fermi level is above in this region EF, then N type semiconductor. If Fermi level is in this region EF, then P type semiconductor. Okay, but we know, when we dope the semiconductor, we know what type of dopants we are adding. If we are adding N type dopants or P type dopants. Okay, so if the dopant is donating an electron, okay, if dopant is donating an electron, or if dopant, these are like, if we say the silicon semiconductor, that which is the highly used Si, silicon. Okay, if silicon has the 4 bonds, okay, if we are doping it with the 5 pentavalent atom, so which has, this is any atom like phosphorus, we are saying, so phosphorus has 5 electrons in the valency shell. So if we replace this silicon with phosphorus, so 4 of the electrons will bond with the other silicon atoms. Okay, other silicon atoms, but there will be always one with every atom of phosphorus added to the lattice, so there will be one electron in the valency shell that will be in the that will be left out, and that will be unbonded with any silicon. So it will move in the lattice. So how it will move? So the ionization energy, or to take out from the to take out this electron from the valency cell, the energy to take out this electron from the valency cell will be very less, because all other electrons are bounded, but this is unbounded. So this energy will be very less, and this can move freely at room temperature. Okay, so when we dope this with pentavalent, so more number of electrons will be there. So this is n type. Okay, so if it is electron donor, we call it Nd. Number of Nd, we represent number of this dopant density. Okay, dopant density of dopants in the lattice. Okay, so they will create an energy level. The energy level of these dopants will be just below the conduction band, because they are donating the electrons in the conduction band. Okay, so the difference between this Ed and Ec will be the ionization energy, the energy of the electron to take out from this bound state to the free state. This is the ionization energy, we can say ionization energy. Okay, so we know this Nd, and now also what we know is, okay, so in the conduction band, this is the conduction band, this is the valency band. What we know is the number of dopants Nd, and at this Ec minus Ed is very less, very less. Almost it is like, we can say, less than, which is less than the energy 0.026 electron volts. Okay, this is the kBt, the energy at room temperature. Okay, the thermal energy, we say it is the thermal energy that which is at the room temperature, kB, which changes. This is the thermal energy. kBt is nothing but the thermal energy, and at room temperature it is 0.026 electron volts at 300 Kelvin. Okay, it is 0.026 electron volts. If Ec minus Ed is less than 0.026 electron volts, then all the Nd, this dopant atoms which we added, they will transfer the electron to the conduction band. That is, the number of electrons N will be equal to Nd plus. Okay, so the Fermi energy that we have seen, the Fermi energy is the consequence of the electrons in the conduction band, the consequence of the moving electrons. Okay, so we know, and reverse is not true. Reverse is not true means the electrons in the conduction band are not because of the Fermi level is above Ei. Okay, Ei it is, and this is the Ef. Ef is here because the electrons are here. The reverse is not true. Reverse is not true means first electrons will be there, then only the Fermi energy will be here, we can say. Okay, I don't know how to make you understand in this case. Anyone has doubt in this one? Are you getting me or not? Like, Okay. Because we doped the semiconductor, then only the Fermi level is moving up. That's it. We are doping the semiconductor, then only the Fermi level is moving. The electrons, because we doped the semiconductor now, that's why the Fermi level is going above, up. Okay. So first what happened, doped the semiconductor, then electrons come, and then Fermi level move. So all uh, this is the thing. Okay, so it is not the thing like Fermi level moved up and that is why the electrons are there. No. Okay, this is not. And the same thing happens with the holes. If the Fermi level is in between this one, there will be the holes in the valency band, and because the holes will be the valency band, and that's why the Fermi level is below the EI. And more and more it will move towards the bands, or towards the conduction band or the valency band, then more and more number of the free electrons or free holes respectively will be in the conduction band and the valency band. Okay. Okay. Arabinda, Arabinda, you can unmute yourself and ask the question. You raised the hand, right, Arabinda?
Sir, I have sir one question, sir.
Arabinda, bolo.
If sir temperature is changes or gradually increases, then if Fermi level positions are also be changed.
Fermi level is dependent on, okay, for intrinsic or extrinsic. Okay, that we
Sir,
will.
intrinsic.
For intrinsic Fermi level will not change. No, never. Because, okay, so let me tell you why the with the temperature it won't change. Okay. Okay, so for intrinsic semiconductor, this is the conduction band, and this is the valency band. Okay, and this is EI, intrinsic Fermi level. Okay, this EI is the intrinsic Fermi level. Okay, so what we have seen is this is F of E. F of E is not related to this valency band and conduction band. Okay, and this is, I am writing a different thing. This is energy E above in the vertical axis. So let me take the another pen, red. Okay, so FE the, okay, this is 1. Okay, this Fermi function, I am drawing the Fermi function. Okay, with the temperature at 0 Kelvin, the Fermi function will be like this. Okay, are you getting? Hello?
Yes, sir.
At 0 Kelvin, the Fermi function will be like this. Okay, so in the valency band will be the full of electrons. There will be no electrons in the conduction band, because the probability of finding an electron above EI is 0. Okay, as we increase the temperature, there will be some smearing out. Okay, as we increase the temperature more, the smearing out will be more. Okay, this direction is the temperature is increasing. Okay, Arvinda. So what will happen is, so whatever the there was a density of states function, this density of state function. Okay, here also there was a density of state function for in the valency band, and this is the in the conduction band. So the this the product of this and this will be same, 1 minus Fe. Here will be the 1 minus Fe. Okay, so the 1 minus Fe is nothing but this part, 1 minus Fe into this Ge will be equal to this Fe into Ge. Ge in the this conduction band, this is the for electrons, this is for the holes P. Okay, these will be equal, there won't be any difference. That's why the number of electrons in this one N and P will be equal. For intrinsic, there be N is equal to P, right? We know Ni is equal to P.
Yes, sir.
Pi. So if the number of electrons will be equal, they have to be equal. So this Fermi level should not vary for the intrinsic semiconductor. Okay. But
okay, sir.
Yeah, actually this varies a little because it depends this Ge. We are taking this in ideal condition, but this Ge will be depending on the M star. Okay, M star, MP star, and this will depend on the Mn star, and these all depend on the temperature. Okay, these all depend on the temperature. So this graph will be not equal to this graph. They are not the mirror images. Okay. Hello, are you getting me?
Yes, sir. Yes,
okay.
Sir.
Okay, let me open the next slide, and here. So ideally, if these are same, then it should not. But in some cases, it happens. This changes a very little bit, not that much actually. Because now I am telling you the density of states function. Okay, this is the one density of states function for the conduction band, and this is this, like this. Okay, another one is a bit different. So initially when there was, this is Ei. Okay, this is Ei. So this Ei arranges itself such that Ni should be equal to Npi. Okay, this Ei arranges itself. Okay, Ei arranges itself. It can be slightly above the middle of middle of the band gap. Okay, it can be slightly above or below. Okay, so when we increase the temperature, if this what should I say, this overlap is more than this overlap. Okay, if we increase the temperature, if this overlap is more, so then the Fermi level will shift a slightly at downwards, so that this product of this Fermi function with this Ge should be equal to the product of this Ge and 1 minus Fe. Okay, with increase in temperature is just slightly shifts, not that much. Okay, but we in our practical, in our purposes, we don't take that much into the account. Okay, but because of this the density of states, this function varies with Mn star, this density of states in the conduction band density of, and this varies with the Mp star. Okay, so definitely there will be a slightly above or below. This Fermi energy will be not in exactly in the middle, but will be above or below. That will adjust itself such that Ni is equal to Pi. Are you getting?
Yes, sir.
It will, the Fermi level will adjust itself according to N or P P concentrations. Okay.
Okay, sir.
हाँ हाँ. हाँ. Okay, n is equal to p. Okay, another one. So okay, what we have studied is n is equal to, let me change the pen. N is equal to nc of nc into, okay, now we are taking into account that our for our this ec minus ef is greater than kb, is greater than 3 kbt. Okay, that consideration I was telling you about, so that we can simplify our integration. Okay, so if we do that thing, so it was, okay, just 11 nc into f 1 by 2, it is ec minus ef by kbt. Okay, so if this holds true, ec minus ef is greater than 3 kbt. Okay, so what will happen is, so we can, this can be this function, this f of 1 by 2 ec minus this Fermi integral can be by kbt, can be approximated to exponential of ec minus ef by kbt. Okay, this Fermi function, okay, someone, this Fermi function can be approximated to this one. So n is equal to nc exponential of ec minus ef by kbt. Okay, yeah. Okay, so now, and p also, p can be written as nv is nothing but the effective density of states in the in the valency band. Okay, and this is exponential of this ef minus ev by kbt. Okay, I will tell you why ef minus ev and here ec minus ef. So this thing I will tell why it is so. So okay, so this is the conduction band, this is the valency band, and what we are taking, this is the ef and ec, this is ev. So nc is approximately equal of the range of 10 raised to power 19 per centimeter cube. Okay, per centimeter cube per electron volt. This is the per centimeter cube effective density of states, yeah, per electron volt. So this is per electron volt or not, this is not, whatever. So ec, the so if we multiply nc in something with something exponential of if it would be positive, this if the integral exponential of something will be positive, so it will go like, it will go exponential of something positive, it will be too much. So, but our density of the atoms will be 10 raised to power 23, Avogadro's number. So it cannot beyond that. It even cannot beyond this NC, because density of states itself is the maximum limit of the electrons that can be occupied. Okay, so and that too when the probability of finding an electron at this at any energy level is 100%, and 100% will be happen when the this Fermi level is above the EC. This EF is above that EC. That will behave like a conductor only, nothing but a conductor. So that does not happen. We do not dope the semiconductor that much. Okay, so this exponential should be negative. When this exponential will be negative, when there will be this EC minus EF will be negative. Okay, this okay, so this is when we go actually what we see is minus of EC minus EF, you can say, or I think this is EC minus EF now. Actually I wrote it wrong in the last slide. It should be EF minus EC, EF minus EC, because it should be negative. This should be negative. Above we are going, E is increasing in the above direction, so EF minus EC will be negative. Okay, EF minus EC will be negative, and then only we can our product will be less than this NC. Okay, so this should always be negative. This exponential of this should always be negative, EF minus EC by KBT. Okay, so take care of that thing. So whether it will be EF minus EV or EV minus EF, so take care of that thing. So this is EF minus EC, and I think in the last slide okay, EF minus EV. Okay, this will be EV minus EF, EV minus EF. So it should be negative, and this is EF minus EC, EF minus EC. Actually that when you will solve the questions now, you will understand that thing. So if it is it should be negative only, then you won't get the answer actually. So our N, okay, now N is equal to EV minus EF. N is equal to NC into exponential of EF minus EC divided by KBT. Okay, and P is equal to NV into exponential of EV minus EF by KBT. Okay, let me, someone wants to join. Okay, so now at any N into P. So at for intrinsic semiconductor, N is equal to P. Okay, is equal to Ni, we can say. Okay, N is equal to P. So from here there are two things we can calculate. We can calculate the Fermi energy level. Where will be the Fermi energy level? So you are asking me about that Fermi level moves or not with the temperature. So this relation, so we can find out by equating these. N is equal to P. Here we can calculate the position of the Fermi level. Okay, you will find that there will be a slight dependence of with the temperature, so that we do not consider in our practical purposes. Okay, and another thing is, if we multiply these two, N multiply P, is equal to, what will happen, Nc into Nv will into exponential of EF minus EC multiply, if we multiply these whatever in the exponentials, they will add up, okay, plus EV minus EF by KBT. Okay, this is EV, this is EF. So they will add up. So N into P is equal to Nc into Nv into exponential of, so what was there, okay, what was there, it was EF minus EC. This EF will cancel out, okay, so what will be left is minus of EC minus EV. What will be left is minus of EC minus EV divided by KBT. Okay, so N into P is equal to Nc into Nv into exponential of EC minus EV is nothing but this is the band gap, minus of EG divided by KBT. Okay, so and N and P, N is equal to P is equal to Ni. This is the intrinsic carrier concentration. Intrinsic carrier concentration is we have not doped the semiconductor, so that's why N will always be equal to P for the intrinsic at equilibrium. So this is the Ni square is equal to Nc into Nv into exponential of negative of Eg divided by KBT. So from the band gap itself you can calculate the intrinsic carrier concentration. Okay, Ni is equal to nothing but square root of NcNv and exponential of minus of Eg divided by 2 KBT. 2, okay, someone came. So 2 KBT. Okay, so for any semiconductor you, if you are given with the band gap, you can calculate the intrinsic carrier concentration. Ni is nothing but the intrinsic carrier concentration. Intrinsic carrier concentration is when the number of holes is equal to number of electrons. When we are not biasing the semiconductor, we are not externally giving something like doping, or we are not stimulating it with the light or anything. Okay, we are not giving any external stimuli. So at that, which is we say the equilibrium. At equilibrium, the intrinsic carrier concentration depends on the band gap. This is the band gap. So this is the relationship. Okay. So if you have any doubt with this particular thing, you can ask me, so I can tell you. Okay. So there are some things with the semiconductors, like why semiconductors are used, because of we can tune the conductivity. So as we have seen, this concentration Ni is equal to n square root of NC into NV into exponential of minus of Eg divided by 2 kBt. Okay, so this depends on the Ni with the band gap. So if the material has lower band gap or higher band gap, what is the intrinsic carrier concentration? So if the materials, so for lower band gap materials, the carrier concentration is very high. So if the for material gap is very less, Eg is less. Okay, so Ni will be very high. Okay, Eg is less, Ni will be high. So tunability of the electrons of the carrier concentration is very less. So if it itself is 10 raised to power 15 per centimeter cube. Okay, so if it itself is 10 raised to power 15 and which is Avogadro number is 23. So if it itself is 10 raised to power 15, so we cannot tune the conductivity that much. Okay, for lower band gap semiconductors, for lower band gap semiconductor, if and in another case, if the so this Eg is very high, Eg is high. Okay, Eg is high. So what can happen? This 10 raised to power 6 or 5, this carrier concentration, intrinsic carrier concentration can be 10 raised to power 6, 10 raised to power 5. So there is a very huge scope of tuning the conductivity of the material. So if the this is like kBt at 0.026 electron volts. Okay, this kBt. So if we increase the temperature, this intrinsic carrier concentration will increase. This intrinsic carrier concentration will increase, and at whatever so do you know about the leakage current? That leakage current in any device is because of this intrinsic carrier concentration only. Okay, so when in the electronics, what happens is the heating of the devices is the main issue. So if the devices heats up, so the current is not the same as it was at the room temperature. So there will be a leakage current. The leakage current will be because of these Ni. So that will be more. Okay, so but for the higher band gap semiconductors like zinc oxide, gallium nitride. So for high band gap semiconductors, this will be there will be a very slight difference between the this leakage currents. Okay, because as we increase the temperature, this intrinsic carrier concentration won't increase that much. Okay, so we just deviated a slide. Okay, I'm just covering the portion that sir already covered, and I'm just covering just because you can ask the questions. Okay, if you will ask me a question, I can go more deeper and deeper into that particular part. So I am assuming you all have watched the videos. So if you have watched the videos, you will only understand all these things. And if you didn't understand in that portion, you can ask me. Okay, so these are the things. Okay. One more thing he has taught is like okay. Okay. So whenever we see the band diagram, like this is EC, this is EV. Whenever we see the band diagram, there is a flat band diagram. Okay. So and this is EI or EF, we say, for intrinsic semiconductor. AD is in the middle. So whenever there is something like this, so we say that this is in the equilibrium. So at equilibrium, what happens is there is no field or no externally given, we are not shining it with the light, because when we shine it with the light, if the energy of the light is greater than the band gap of this one, uh, when the energy of light is greater, then there will be a generation of the electrons and holes in this, in the semiconductor. So n will not be equal to ni. Ni is when we are not shining the light, we are, that is in the dark condition at room temperature. Okay, so if we are shining the light, we are generating the electrons and holes, but at this point n will be equal to p when we are shining the light, because we are shining the we are generating the holes and electrons from the semiconductor itself. We are not injecting the holes and electrons from the outside. Okay, so there will always be n is equal to p at this point. But if we are doping the semiconductor, this n will be different and p will be different. If we are doping the semiconductor with n type, so this is the EF, so it is the n type, so in this one n will be greater than p. Okay, so if we are shining the light, that will be n plus delta n, n plus delta n, and this will be p plus delta p. Okay, when we are shining the light, okay, when we are shining the light, this will be n plus delta n and p plus delta p. It will, because in this case delta n is equal to delta p, because delta n is equal to delta p. Delta n is the extra electrons or extra holes that are created, that are generated because of the light. Okay, so these they will be equal, because when there will be a generation of holes inside a semiconductor, then there will be a it will be going from this part, electron is going from this point to in the from the valency band to the conduction band. Okay, electron jumped from this is the electron hole pair that is generated because of the shining of the light. So if there are n delta n number of electrons that are transited from the valency band to the conduction band, so delta n, okay, so there will be delta p, this number of holes generated in the valency band. Okay, so this is the thing, this is the new thing that is not covered in the lecture. Okay, and another thing is, so if there is a gradient in the in the valency band or the conduction band, so if the conduction band or valency band are like this, okay, and the Fermi energy is something which is constant. Let us say this is the constant. Fermi energy is constant, this is not varying. Okay, this is EF, this is EC, this is EV. So if there is gradient, this is gradient in the sense there is slope in the conduction band, then that same slope will be in the EV. Okay, EV, because the band gap will remain constant, whatever be the thing, band gap won't change. Okay, band gap won't change, so band gap will be the constant. So if there is this is because of the potential, this is nothing, this energy energy E is nothing but the potential. Because of the potential, if there is changing, then potential is what? Potential is nothing, that is because of the field. Okay, the energy field. So if there is a gradient, okay, this energy E and potential, how should I represent that, is, let us say, V. Okay, potential V. Okay, someone wants to join. Huh. Huh. So potential V and okay, energy, potential, and field, electric field, let us represent it by psi. So these all are related. Okay, so whenever there is change, there is a change in the, there is slope in the conduction band or the valency band, then there is a there is a field in that semiconductor. This is the x axis, okay, or this is the real space. Okay, if there is a gradient, there is a slope in the conduction band or the valency band, then there will be a electric field. Okay, and if there is a gradient in the E, this Fermi level, then that is represented by the, if there is current flowing in the semiconductor, that is represented by the, there is a slope in the Fermi level. This is the EF. Okay, so these are some things. Someone. Okay. 14th and 15th. So okay, one more thing I will just cover is 17. Okay. Sir, also, if one more thing he has covered is what if this is the semiconductor. Okay, this is the semiconductor. If we dope it with the n type as well as with the p type, so what will happen? So there are some consequences also. So if these are known as the compensating semiconductors. So if we are doped with nd, this is the donor atoms with the phosphorus or something, and also with the Na acceptor, with this is the n type n doping, and this is for the p doping. Okay, Na is the acceptor and Nd is the donor. Okay, donor means that we are increasing the number of electrons. Acceptor, it is accepting the electron and converting to Na minus. Okay, it is accepting the electron, means it is creating a hole in the semiconductor. Okay, it is this one is donating the electron, that means it is creating the electron in the semiconductor, in the lattice. So it is Nd and it is Na. And if we are doping, we have doped the semiconductor, let us say we have doped the semiconductor with Nd is equal to 10 raised to power 17. Okay, we have doped this semiconductor with 10 raised to power 17 atoms of this donor atoms per centimeter cube. Okay, so but now we want this semiconductor to behave as a p type. Okay, so whenever we make the PN junction, no, so how do we make the PN junction is this. Okay, just yeah, someone is asking to join. So, okay, whenever we make the PN junction, na, what we make is if this is a P type wafer or a N type wafer. If it is a P type wafer, okay, let us say this is a N type because we have shown this N type wafer. Okay, so ND is equal to 10 raised to power 17. Let us say this is the P type wafer, N type wafer, and ND is equal to 10 raised to power 17. So many people are coming and going. So this is this is 10 raised to power 7, but we want to make a diode with the PN junction. So what we will do is we will cover this surface with the there will be oxide with the oxide or with something, some photoresist with through the lithography. We will do that, and we will dope this one with the P type. With the boron we will dope this one, and what we will make is we will remove this one later. So what we will get is this is N type it was, and here we have doped this heavily, which was N A is equal to 10 raised to power 18, 10 raised to power let us say it should finally come 10 raised to power 17, right? So 10 raised to power 17 with 10 raised to power 18 we will dope. What will happen is okay, Na with 2 into 10 raised to power 17. If we will dope it 2 into 10 raised to power 17 with the boron atoms, okay, so it will compensate 10 raised to power 17 atoms of this phosphorus first, and this extra boron will act as a p dopant. First it will compensate, and then the extra will act as the p type. Okay, so this will make an NP junction, PN junction, or P this is the same thing, NP or PN, that is the same thing. PN junction it will make. So it will make a diode. How we make it? We compensate the extra dopants. Okay, so we don't do that. We make the there is a wafer, we have P type here, N type here. We don't do that. No. So that is too much process consuming. First, that will increase the number of steps, and if we are increasing the number of steps to fabricate any device, to make a device, so it will increase the cost of that device. Okay, so to reduce these things, so it has other effects also that I will tell you. What are the other effects? So that has not been covered. I don't know it will be covered or not, but it will be covered in next section when there will be a charge transportation. So there will be scattering. You must have heard about that. If there are more number of people in the street, if I am going in through the street, so I will encounter more number of people, then I will get slow down. Okay, if more and more number of people are there in the street, I will go slowly. If less number of people are there, I can go fast. So if okay, ND was 10 raised to power 17 already, and we have doped NA with 10 raised to power 2 into 10 raised to power 17. So it will compensate this one 10 raised to power 17, and Na effectively Na will be 10 raised to power 17 only. Like P is equal to that number of holes will be 10 raised to power 17. Okay, but there will be ionized atoms. This ND will be there, Na will be there, which are already ionized. the concentration of the ionized atoms will be 2 into 10 raised to power 17. These much atoms are extra in the lattice. Okay, these much atoms are extra in the lattice. So whenever any electron and this hole will be going through the lattice, it will encounter it will encounter with these lattice with these atoms. If it will encounter, it will get slow down. Okay, it will get slow down, the mobility will decrease. If the mobility will decrease, conductivity will also decrease. Okay, so whatever, if we are saving the cost of the device, we are uh, also losing something. So there is an optimum thing. So how we like cost should also be minimum, and device should work with the optimum parameters. Okay, optimum can say mobility or conductivity. Uh, so so if how we are compensating that is, I will briefly I can tell you. So there are ND and there is Na. We have doped a semiconductor with first with the donor atoms like with phosphorus, and secondly with the boron atoms with acceptor ones. So what will happen is, at room temperature we are assuming a complete ionization. Okay, so complete ionization is the each dopant Nd will give me an electron N. Okay, so all will be ionized. So Nd will be completely ionized, and we can say that is equal to N. Okay, or if it is not completely ionized, but completely ionized or not completely ionized, our whatever we are going to derive, uh, uh, that will be applicable if it is ionized or not ionized. But we will need the values of this, how what is the extent of ionization has happened at that particular temperature, because this Nd changes into Nd plus electron. Okay, one atom of Nd changes into Nd plus electron, it will donate the electron. Okay, so if here how so if there are Nd number of dopants, okay, and Na number of acceptors, so Nd Nd number of dopants will give us Nd plus okay, it will turn into Nd plus. Okay, so Na will turn into Na minus, and will give us number of holes, and it will give us number of electrons. Okay, so total number of so in an semiconductor or whatever, at equilibrium, the number of holes should always equal to the number of electrons. Okay, so I'm and one another thing I just forgot to tell you is, this Nd plus is nothing but positively charged ions. These are immobile ions, and they does not contribute in the charge conduction. Okay, but they will act as a scatterers. They will decrease the mobility, but they won't increase, they won't contribute in the conduction. So like there are some pillars, they are kind of some pillars in the road. Okay, so they will affect the mobility, they will affect the everything, but they won't contribute. Okay, so total number of electrons n, number of electrons n, these. Okay, the total positive charge should be equal to the total negative charge. Total negative charge in the lattice, if we have doped it with Na plus Na and Nd, so this will convert into Na minus and this will convert into Nd plus. So total negative charge is n plus Na minus. Okay, n plus Na minus will be equal to P plus Nd plus. Okay, so this is the total negative charge in the semiconductor and this is the total positive charge in the semiconductor. Okay, n plus Na minus is equal to P plus Nd plus. Okay, this is the thing. So yes, and okay, one more thing I wanted to see is okay, so here what sir has told is in his lectures, whatever we say. So from here we can calculate if we are given with the incomplete ionization or complete ionization, we can calculate from this this just simple equation, we can calculate. And in this one, the one thing, at equilibrium one more law of mass action, we say Np is equal to Ni square. This will always hold, whatever be the thing, this will always hold at equilibrium. So we can put this thing in here, Np is equal to P is equal to Ni square by N. So we can put here at we can replace P with Ni square by N and with this Na minus and Nd plus. Okay, Nd plus. So if there will be an incomplete ionization also, we can calculate these things. Okay, but in our practical in our semiconductors, we consider a semiconductor is completely ionized with a dopant is completely ionized for when we do the silicon devices. Okay, so we consider that a complete ionization is there, and from here we can calculate the equation. This is a simple mathematics. So if we are considering complete ionization, Na minus will be equal to Na and Nd plus will be equal to Nd. Okay, because of complete ionization, so we know how much we have doped with the acceptor and how much we have doped with the donor. Okay, we can calculate directly. I am not going in the calculation just because we are almost at the time is going to up. So just last thing I will tell is okay. Last thing I will tell is the temperature dependence of the Fermi level with of the extrinsic semiconductor, not the intrinsic semiconductor. Intrinsic semiconductor I already told when someone asked the question. So how this Fermi level or this carrier concentration will depend? We can say that okay, Fermi level also I will tell, and both the things I will tell. Okay, so if we are, let us say okay, this is EC, this is EV, and if we are doping the semiconductor with the whatever, say Nd. Okay, so at lower concentrations, okay, at no, at lower temperatures, okay, at lower temperatures what will happen is Nd will not be completely ionized. So whatever why I was saying that incomplete ionization at lower temperatures, say let's less than 100 Kelvin, 100 Kelvin. So at less than 100 Kelvin, this kBt, this thermal energy is not sufficient for to ionize this completely ionize the donors. Okay, so what will happen is there will be the electrons. Huh. Okay, the electrons in the conduction band, there won't be any electrons in the conduction band at 1 Kelvin, at 0 Kelvin. Okay, at 0 Kelvin. So the graph for, okay, so I am, this is temperature this side and this is the log of N, charge carrier concentration. Okay, for Nd. So at lower temperatures, the this charge carrier concentration will be negligible. Okay, so at lower temperatures, so as we increase the temperature, charge carrier concentration will increase. Okay, so there will be a temperature at T is equal to T naught. There will be a temperature, so at which these will be completely ionized. Okay, these will be completely ionized, and okay, this will go flat. Okay, and when, and there will come a point, and okay, so there is another thing, intrinsic carrier concentration, Ni is also a strongly dependent on temperature, that we have seen that minus of exponential of minus of Eg by 2 kBt. Okay, this is also dependent on temperature. So Ni will come like this. Okay, Ni, this Ni. So it was constant for, this was because of the Nd plus Nd. This value is nothing but log of Nd. This value is nothing but log of Nd. So after that comes the Ni. This region is because of the Ni, log of Ni. Okay, so this is the intrinsic region. Okay, this region is just because of the intrinsic carrier concentration, that are because of the higher temperature. This temperature, at higher temperatures, at these moderate temperatures, all these donor atoms are ionized in this region, and in this region partial ionization. Okay, partial ionization. If there will be partial ionization, so Nd N okay, this N won't be equal to Nd. Okay, this N won't be equal to Nd, but N is equal to Nd plus. Nd plus is nothing but the partial ionization. Okay, Nd plus is not equal to Nd and will also not equal to N. Okay, so and another thing I want to tell you about this Fermi level, how this Fermi level with the temperature, how that depends on the temperature. Okay, how can I tell? Okay, let me see once. Not I'm actually, let me just gather my thoughts on this thing. Okay, we both will do that how this Fermi level will depend on the temperature. Okay, this is not the gradient actually. Okay, this is not the gradient, so this is flat only. Okay, so at higher temperatures, when T is very greater than T naught, T naught is nothing but uh, when intrinsic, okay, T naught, in this one, this is the T naught when it started behaving like an intrinsic semiconductor. Okay, so T naught, at T naught, the Fermi level will be the in at this point, Eg, EF, EF is equal to EI, because there for intrinsic semiconductor there will be holes will be equal, number of holes will be equal to the number of electrons, so the Fermi level will lie at the middle. Okay, so Fermi, for T is greater than T naught, for this region it will be in the middle. The region before this, okay, in this region what will happen is the Fermi level will be above, the Fermi level will be above this thing, above क्या बोले, in the middle. Okay, EF for this for this extrinsic region, we call it then extrinsic region. For this region, this EF will be here. Okay, EF will be here. And in this region, how it is going, the number of electrons are increasing and increasing. Okay. But I need to check this one once. So how this Fermi level will behave for freeze out region? That was the freeze out region. But for sure that at lower temperatures this Fermi level will be above the EI. Okay, Fermi level will above EI, that is definitely for n-type semiconductors. Okay, for n-type semiconductors, and for p-type it will be below. For p-type semiconductors the Fermi level will be below at temperatures which are not greater than the when it starts behaving with like an intrinsic semiconductor. Okay, so okay, anyone has doubt in till now? Because I can feel that this session was a bit more confusing. So if anyone has any doubt in this one, so they can ask me. You can ask me. Okay. Differentiate between drift and diffusion current. Okay, someone has asked the questions, so you guys can ask me directly because I cannot see the questions here. Okay, anyone has the questions? Now you can unmute yourself and you can ask the question. If no one has the question, so we can stop today. Okay, so you can leave. Thank you for attending.
Thank you, sir.
Yeah, thank you.